thank you for having me to your lovely church. I hope that you all can keep your appetites as I go ahead with this presentation.
He's not joking.
Today we're going to talk about a little bit about my background and a little bit of background mathematical physics. Hopefully not too much. I don't want to blind you with too much math. We're going to talk a little bit about overfishing in the oceans, which is a subject that people are somewhat familiar with, I find. Then we're going to talk about a subject that people are less familiar with, the great elemental cycles that drive the biosphere. And then we'll talk about the prospects for the future. My name's Jim Galveston. I have an electrical engineering degree from MIT. I'm not an expert in any of the subjects I'm going to talk about today, but I do have some expertise in system theory and in signal analysis, which I try to bring to bear on some of the data that I'm going to be showing you. What I do is I can read a scientific paper and I extract the data from scientific papers, and then I present that data to the public in presentations like this and also on my blog, so that people can be exposed to what's happening with the most recent scientific findings. Then we'll talk a little bit about what influenced me as a child. So in the early 1970s, after the hippie revolution failed, a number of film dystopias were released, and from the ridiculous, like Logan's Run, to the sublime Soylent Green, which is possibly the most prescient film ever made, successfully predicting overpopulated megacities, global warming, and the destruction of the oceans. This was very influential when I saw this film on me in the middle of the 1970s. How did we get where we are? This quote probably explains it better than any that I could dig up. Human beings do not understand exponential growth. Exponential growth occurs in systems in which the rate of change of the system is dependent on a current value, some current value. So think about compound interest as an example of exponential growth. This is a particular exponential growth function called the natural exponential growth, because the number e is the base of the exponent. E is called the natural logarithm. It's a number like pi. It's equal to about 2.7128. And as you can see, as we progress along the bottom axis, the function itself increases very rapidly once you get past the mean, as it's sometimes called, right here. There's also exponential decline, or decay, which is the inverse if you flip the horizontal axis. And the reason I'm showing you these functions is because they're very important in a set of mathematical physical equations called differential equations, which I'm going to show you a little bit about. And the reason those are important is because they describe ecosystems. They describe the dynamics between predator and prey species. So for example, we have a prey population on the left, we have a predator population on the right. The prey population is influenced by the population of predators. The population of predators is influenced by the population of prey. There's a particular mathematical relationship that describes this relationship. And you can look at the rate of change in the prey population over here is equal to the increase in the prey population minus the number of prey killed by predators. Similarly, the predator population is controlled by an equation that's dependent on the prey population. So predator population equals the reproduction rate of the predators minus the number of predator deaths from starvation. What's important about these equations, I don't want to throw a bunch of math in your face, but these are the solutions, the general closed form solution to those equations, only discovered in 1988. And the important feature that I want to show you is that the number E is fundamental to describing population dynamics between predator species and prey species. The real world, when we integrate those equations, you can see this is a nice stable ecosystem between a simulated hare population, snowshoe hares, and a simulated lynx population. And the important things to note about these solutions is that they're oscillatory. This is a stable ecosystem that's healthy. And what happens is the prey population leads the predator population. So as the hare population declines, the lynx population declines. As the hare population increases, the lynx population increases. If you look at real data, this is data collected from the Hudson's Bay Company from the mid-19th century up into the early 20th century. you can see that the red curve, which is the lynx population, always follows the green curve, which is the snowshoe hare population. And so we know that real-world data match the equations in a way that gives us confidence that we have math that can understand the way predator and prey species interact. Here's another example, the Isle Royale National Park in Michigan. You'll see that as the moose population declines, the wolf population declines. And as the moose population increases, the wolf population increases. And that they are in a nice 50-year cycle or so. These are stable ecosystems, these are healthy ecosystems whenever you see oscillations like this. The real world is a little more complex, so in the marine food web that I'm showing here, this is a simplified diagram of a marine food web, but you can see a number of bigger fish eating smaller fish, predator-prey relationships. The base of the food web comprises phytoplankton, primary producers. These are microscopic organisms that harvest sunlight and convert that energy into matter that's used by the rest of the food web. So without the phytoplankton down here at the base of the food web, there would be no food web. We arrange, in a food web diagram, we arrange them by species by trophic level, and that basically tells you who's eating whom. So here we have large zooplankton, like krill, they dine on phytoplankton. We have small fish dining on the zooplankton. We have the larger fish eating the smaller fish, until we get to the top of the trophic web, where the big fish, say tuna, which are like the cheetahs of the sea, and they eat a number of the other smaller fish. We have marine mammals at the top, which eat the fish, and of course we have humans, and we eat everything underneath us, essentially. So now I'm going to change gears a little bit and talk about the history of ecosystems on Earth. There have been 6 great mass extinction events in the about 550 million years of multicellular life on Earth. A couple of these are interesting. For example, everybody knows about 65 million years ago when an asteroid smacked into the Earth and rendered the dinosaurs extinct. That's called the Cretaceous Tertiary mass extinction event. We're in the midst of the 6th great mass extinction event caused by humans. It's been going on for about the last 10,000 years. He took off the top of the Holocene biosphere by removing saber-toothed tigers, for example, and by mastodons. And this diagram is nice because it shows you what other species are becoming extinct. Great apes. This diagram shows hippos. It would probably be more accurate if it showed rhinos. But the most interesting feature of this diagram is what happened here 250 million years ago. This is the Permian-Triassic mass extinction, also known as the Great Dying. The largest number of species went extinct during that period than at any other time in Earth's history. So it's very interesting to study what happened at that point. I think it's the closest analog to describe what's happening in the Earth today, so I talk about this a lot. At the end of the Permian period, 250 million years ago, there were strong and diverse ecosystems. This is a diagram that shows some of the species that you'd find at the bottom of the ocean floor. It's a benthic ecosystem, meaning that it's on the ocean floor. And you can see a lot of interesting species here. You can see corals and sponges and all of the various life that live in and amongst those species, kind of like the way species live in forests today. After the mass extinction event, this is what the ocean floor would have looked like in the early Triassic. The scale is much smaller. You'll notice the 5-centimeter scale indicated down there. So these are a few very small organisms managed to survive this mass extinction event. Some 90% of ocean species went extinct at that time, like 70% of land species. One of the other important aspects of the Permian-Triassic extinction was how long it lasted, how long it took before biodiversity started to recover. And that's in the neighborhood of 5 to 10 million years. So something very serious happened at the end of the Permian. There were, on land, there were a few survivors. You had to be very tough. You had to be a generalist. This fellow was called a cynodont. And he, one of his relatives, this is Lystrosaurus, and you had to be really tough to survive whatever happened at the end of the Permian. And this is a plant species that they're dining on called Pleuronea, which was a now extinct spore tree. And there was very little other life that actually survived on land. So where are we today with the situation with the oceans? The most obvious feature of what's happening in the oceans today is overfishing. You probably all have heard to some degree or other about sustainably harvested fish species and overfishing, ocean overexploitation. So I'm going to go into a fair amount of detail about what we're doing with the oceans as far as fishing them out. And then we'll talk a little bit more about more subtle problems that we're introducing. You've probably all heard about ocean long lines. These are curtains of hooks that are suspended along a line that can be many miles long, dozens of miles long, suspending thousands of hooks in a curtain that catches everything. They're completely indiscriminate. It's a brutal form of fishing. Sea turtles are taken, marine birds are taken, marine mammals. The bycatch is enormous. So
They're not big, is that correct?
they are baited. And very small boats can go out and release miles of long line, and they'll often use a bycatch to bait the hooks.
What is a bycatch?
Bycatch is a species that's not the target species you're trying to catch. So if you're going out to catch, say, tuna or swordfish, as this diagram shows, bycatch would be seals, dolphins, sharks, anything else that ends up in the long line that you don't actually intend to sell and market. Indeed, collateral damage. Here's an example of the kind of terrible death that many of the animals face when they're caught in pelagic long lines. Pelagic means open ocean. Here's the Sea Shepherd crew. You can see I'm flying the colors today, bringing in a pirate long line. Unfortunately, a great deal of this fishing is illegal, completely unregulated. There are a lot of environmental regulations on the books that are almost completely ignored. Essentially, organized crime sends these ships out and removes biomass from the oceans without any sort of oversight whatsoever. Here's Sea Shepherd crew destroying a long line, a pirate long line. And again, they haul in a couple of miles of line hair and then they burn them on the boat. These photos, by the way, were taken by my lovely wife Isabel when she was crewing. Another form of ocean fishing practice is called bottom trawling. So the long lines are set out in the open ocean. Bottom trawling is done on continental shelves, which are typically the most productive parts of the ocean ecosystem. And as you can see, these nets are very large. For comparison, here's a double-decker bus, and this is typically 30, 40 meters tall net, and it's dragged along the bottom, and all forms of life are consumed in these nets. Again, the amount of bycatch is enormous. Corals are caught, sponges are caught, all sorts of trash fish are caught, and all of that is systematically hauled up and then dumped overboard. How big are these nets? You can see them from space. Here's an example of two boats that are dragging a trawl net. And aside from directly destroying the communities at the bottom of the ocean, they also cause these huge mud trails. And all these mud trails fall out to different parts of the ocean bottom and cover up species like corals that can't tolerate being covered up with sediments. And so it's very bad to increase the turbidity of the water like this. Here's a deep water sponge community off the west coast of Canada before bottom trawling. And here's what it looks like after bottom trawling. It's been completely clear-cut. It's as though you had gone into a forest and just razed the forest. And as you can see, this earlier shot, the depth was 183 meters, and now the depth measures 187 meters. So that's 4 meters, or 12 feet, of mud that's basically been stripped off the bottom of the oceans, and everything that lived in there was destroyed. So to give you an idea of the scale of this kind of activity, here's another satellite view of some Chinese bottom trawlers. This is a very interesting technique where the boats themselves don't actually move through the water. They anchor, and they allow the current to carry all of the creatures into their nets. But as you can see, the effect is the same. Large mud trails are left by these boats. And as you can see, there's lots of them. So this is off of Jiangsu, China. Dozens of trawlers strip mining the bottom of the oceans. And what we've done with this technology is essentially cleared continental shelves of most benthic life. So it's as though you sent these, as though you sent loggers into forests and just chopped everything down for thousands of square miles.
Hey, Jim,
Well, we did that.
do you have data on the percentage of this type of seafloor that's been, like we're always hearing about the percentage of rainforest that's destroyed every year.
Right.
We have
It's
percentages
close
about...
to, it's getting close to 100%. We've basically scraped all of the continental shelves empty and harvesting biomass.
Do we have data on how long recovery takes, or is it just
It
happens
would be
outside?
probably 100 centuries. I mean, those are deep sea species like those sponges that I showed you. They take hundreds of years to grow.
Okay.
And so essentially there is no recovery. You end up with very simplified benthic communities like what I showed you at the beginning of the Triassic. This is shrimp bottom trawling off the coast of Louisiana. You can see that the Americans are somewhat less organized than the Chinese. That's what they do, that's what we do. But the effect is the same. You can see the turbidity of the water has increased greatly. You can see some numbers on how this kind of unrestrained fishing has affected the southern Grand Bank, the coast of Newfoundland. This is a slice of the destruction of the North Atlantic cod fishery, which is still not recovered in spite of quite a few years, probably over a decade of very severe fishing limitations now. And as you can see, cod, skates, flatfish, all sorts of fish we've basically fished out. What's amusing though is when people like from Iceland blame dolphins for this. I always think that's great, or whales, and they use that as an excuse to go out and kill whales. That's always it's like, well, the dolphins and the whales don't have jaws that are thousands of hooks in them. They don't have, nets that are 10 miles long. So it's ridiculous to blame the natural ecosystem for causing this kind of effect. All across the North Atlantic, the blue curves here are fish populations. The red curves are fishing intensity, which is essentially measures the number of hooks in the water. And interestingly, what you'll see is these exponential decays, like what I talked about at the beginning of the presentation, as these populations are fished to extinction. And you can also see exponential increases in the red curves, the number of hooks in the water. So we're essentially acting as a super predator with many, many more teeth than a natural predator would have. And it's a predator that doesn't starve because all of this predation is fed by fossil fuels. Well, what happens when you put millions and millions of hooks into the oceans and fish them out? What happens is what we call trophic cascades. So you start by catching the largest fish. And off the coast of North Carolina, the largest fish were sharks. Sandbar sharks, dusky sharks, tiger sharks. And as you can see, since the 1970s, they've been exponentially decaying toward extinction, all of these shark species. And the numbers right now are typically about 70 to 100 million sharks are taken every year out of the oceans. No species can sustain that rate of predation.
Do people eat them?
No, almost all this is bycatch. There are shark fisheries that supply the Chinese or the Asian shark fin soup market, and so a lot of sharks are taken specifically to feed soup, and all that's taken is the fins. They chop the fins off while they're living and toss them over, and they die a nice horrible death on their way down. But most of this is bycatch. They're just in the way. These sharks just happen to be caught up in those giant long line nets. But what happens when you remove the top layer from your food web, those are the apex predators, and they're very important for keeping the other populations that are on lower trophic levels under control. So for example, the sharks would keep the cow-nosed ray populations off the coast of North Carolina under control. Without the sharks, you see exponential growth and then collapse. Exponential growth, collapse. Exponential growth, collapse. Exponential growth, collapse.
Oh.
Their prey species, the bay scallops, exponential growth, collapse. And now there's nothing off the coast of North Carolina but desert. No sharks, no rays, no scallops. Really? Exactly. Another example of a top-down trophic cascade, and that is, what that means is we're taking the top levels out first of the food web. When industrial whaling came to the Pacific Ocean in the 1950s, as you can see, exponential decay toward almost extinction. Those of you who are old enough may remember the Save the Whale campaign in the 1980s with Jane Fonda. and others. Well, this is the reason that that had to happen, because we almost killed all the whales in the Pacific Ocean. So who feeds on whales? Orcas. Without whales to eat, the orcas turned to harbor seals. And you can see the exponential decay of the harbor seal population in the Pacific. Once the harbor seals were fished out, the orcas went after fur seals. Once the fur seals were fished out, they went after sea lions. And finally, when the sea lions were fished out, the orcas went after sea otters. And a sea otter is basically a snack to an orca. Orcas have to eat many, many sea otters to keep their caloric intake up. Once the sea otter population crashed, their prey, the sea urchins, in the North Pacific went out of control, and they devoured the North Pacific kelp forests, which was another way of clear-cutting a benthic ocean community, was by having urchins go out of control and eat all of the kelp. This phenomenon is called fishing down the food web, and what the orcas did in that trophic cascade that I just showed you is exactly what we are doing. And we're removing all of the biggest fish from the oceans. About 90% of tuna and other big fish are now gone. And now we're fishing in the open oceans for sort of these mid-sized fish. And when they're gone, and they're well on their way to being gone, we'll be left with very small fish and, as you commented, jellies. There are opportunistic species who will move in to fill some of those nodes in the food web, but they tend to be jellies and squid and other not so powerful creatures. So that's the assault on the oceans from the top of the food web down. There's the other way. You can go upward through the food web and cause an upward trophic cascade. So at the base of the food web, we have phytoplankton. These are chlorophyll-carrying, photosynthesizing creatures, microscopic creatures, and they are responsible for keeping the entire food web alive. Well, what's happening to marine plankton, sadly, is they're in decline in every ocean on Earth. The Arctic Ocean clearly in decline, the Pacific Ocean, the Atlantic Ocean, and the Southern Ocean. Although this is an interesting spike here, an exponential spike in the Southern Ocean. Usually when you see unrestrained exponential growth or decay, your system is really messed up. We should be seeing these oscillations, which represent a healthy ecosystem. But instead, when you see these sorts of curves that are going way up and then crashing, you know that something is seriously out of whack with the system. Predators of phytoplankton are zooplankton, for example, krill. And unfortunately, krill are also in decline. In the Southern Ocean, for example, this is a logarithmic scale, so this is each notch is a factor of 10. And as you can see, the krill population is declining drastically in the Southern Ocean. Here up in North and Antarctica, the krill population is in severe decline. I have another graph that goes with this, and I'm not showing, that shows jellies and salps, which are jellyfish-like creatures that are moving in to take over. And when jellies take over, most fish don't eat jellies, and so that's a sign that your ecosystem is in really serious trouble. There's an outfit called the Census of Marine Life that does a lot of great work, and they have a project that tries to ascertain the historical populations of sea life. In this case, they're trying to look at the historical populations of abalone, and they do that by looking at the price of particular fish on the food market. And in this case, this is San Francisco abalone prices going back to 1920. And as you can see, this exponential increase in price followed by collapse gives you an idea of how overfished abalone has become. Right now, the price is around $7, I think, a pound, according to the Census of Marine Life. And so from this, you can infer that we fished out abalone as well. And abalone are also at the bottom, or near the bottom of the food web. There's a lot of creatures that would eat them. They could.
Hey Jim, I'm not sure I understand. Why are they cheap now if they're very scarce?
Demand collapsed. You just couldn't find them. Right? And that's my understanding.
Oh, okay.
So globally, you can see a general trend declining in cod populations. A lot of this is driven by the decline in the North Atlantic cod fishery collapse. Here's the tuna curve that's peaked and is now declining. These other fish that are lower in the trophic web seem to have peaked and are now declining. And
Jim?
Yes, sir.
Those curves were how much were caught, not populations?
Yeah, this is take.
This is take.
Right. So I have another graph that I didn't add in shows the take per person globally, which peaked in 1988. And so there was never more fish protein being extracted from the ocean per person than in 1988, and the curve is rapidly declining now, because the population, of course, the human population is, of course, increasing greatly. So overfishing is the obvious thing to talk about when you're talking about the state of the oceans, but I recently have taken a different attitude, a different tack toward the problem. And I think the bigger problem that we face is disturbing the great biogeochemical cycles on which all life depends. The entire Earth biosphere depends on these elements: phosphorus, nitrogen, sulfur, carbon, some others. These are the ones I'm going to talk about, mostly phosphorus, nitrogen, and carbon today. And when we knock those cycles out of sync, things happen to the biosphere. For example, when we add too much phosphorus, eutrophication occurs. Eutrophication happens when there's a bloom of microorganisms like algae, and then they die, and during their decomposition, oxygen is removed from the water by the bacteria that do the decomposing. Nitrogen also has that effect. Nitrogen also can produce acid rain on land. Similarly, sulfur emissions can produce acid rain on land. And carbon can do all sorts of unfortunate things. These numbers are actually hard to come by, so this was probably the hardest slide to put together in this whole presentation, was estimating the amount of these various elements that we are dumping into the environment. Nitrogen, active nitrogen, is about 80 million tons per year. Sulfur, we're dumping over 100 million tons per year, mostly from burning fossil fuels. Phosphorus is somewhere in the range of 9 to 30 million tons per year, which is a much smaller number, but phosphorus is usually the limiting nutrient in any system. You need phosphorus to build your DNA, and you need phosphorus to do basic metabolism with ATP and ADP. So phosphorus, when it's added to the system, it has the biggest bang for the buck. It causes the greatest change immediately in an ecosystem. And finally, of course, carbon. The size of the carbon disturbance is around 9,000 megatons per year. So we're emitting about 9 gigatons of carbon into the atmosphere and oceans every year as a result of fossil fuel burning. Yes, sir?
But you need to emphasize the fact that that's anthropogenic.
All of this is anthropogenic. All of these emissions. Yes, humans are responsible for liberating all of this matter from the lithosphere, from the crust, where it's been safely sequestered for millions of years, typically, and we demineralize it. We turn it into a bio-accessible form, and then dump that active element into the environment. If you wonder how it's possible for us to be dumping billions of tons of these pollutants into the environment, this is an interesting map I found showing the amount of earth moved by humans on the top and naturally by rivers on the bottom. The scale on the left is 0.1 gigatons per year, so it only takes 10 years to hit 1 gigaton at any particular point. So here you see this is Appalachia mountaintop removal, and that means coal mining. All of this in here is coal mining. And as you can see, we move much more earth than all of the rivers in the western United States together. And the reason we can do that, again, is that we use fossil fuels. How do we emit these elements into the environment? Well, there's a number of ways we do it. We emit carbon dioxide from deforestation and from burning fossil fuels. We emit reactive nitrogen from agriculture, and we also emit phosphorus from agriculture and other organic pollutants. And these have various unfortunate effects on the ocean and the deep ocean and the coastal ocean. I'm not going to go into detail with that diagram, but that gives you an idea of what we're doing. To show you how powerful phosphorus is, here's an experiment that was done in Canada a number of years ago. Scientists took a lake and divided it in half by putting a curtain in between the two halves of the lake. They added carbon and nitrogen to one side of the lake, and they added carbon, nitrogen, and phosphorus to the other side. And as you can see, the algae bloom that occurred was entirely dependent on the amount of phosphorus that was added. Presumably, after this experiment was done, all of this algae died and sunk to the bottom and probably seriously affected oxygen levels in the lake for quite a long time. A less intentional experiment is Chesapeake Bay. You can see what's happened to the waters of Chesapeake Bay because of all the phosphorus that's running off of the agricultural lands upstream. Similarly, Lake Erie, you can see this very large algae bloom, probably the largest in history, or one of the largest in history, caused recently in the last few years, probably because migrations into Lake Erie. And the granddaddy of algae blooms is here in the Baltic Sea. 7 of the world's 10 largest dead zones are here in the Baltic Sea. This is Sweden over here, and this is Latvia here, and Lithuania. And what you're looking at here is an algae bloom driven largely by phosphorus and reactive nitrogen. And these waters are some of the most severely anoxic in the world, meaning that there's very little oxygen in the water there. Anything that needs oxygen to survive dies there. In addition, the metabolism of these sorts of organisms often emits neurotoxins or some sort of toxic molecules that can poison any sea life that's in there, and it can get bad enough, like off the coast of Florida, you can get red tides that will produce a neurotoxin that make people sick and kill their pets. And if you're a manatee swimming around in there, I try to go easy on the gruesome photos in this presentation, but I do have photos of manatees with blood pouring out of their eyes and ears as a result of the neurotoxins that come out of these sorts of algae blooms. So here's the exceedance of acceptable levels of phosphorus around Chesapeake Bay. All of this excess phosphorus that's added for agriculture washes into Chesapeake Bay, causing it to be almost completely anoxic. So the red zone there is essentially, there's no oxygen for any kind of creature that needs oxygen, nothing can live there. Similarly, with nitrogen, we have a huge amount of nitrogen being emitted. I like this graph because it's fairly detailed and it shows you what's happening in Spain. And so this is, if you integrate over that whole area, it's millions of tons of nitrogen being emitted from Spain and Europe. As you can see, the amount of nitrogen that's being emitted has been increasing since the beginning of the 20th century. This is measuring actually the number of nitrophilous plants like lichens and mosses. And they're loving what we're doing. We're dumping so much reactive nitrogen onto our fields, then that nitrogen lands into nearby forests, nearby watersheds, and creatures that like nitrogen like this are loving what we're doing. Europe, the situation is no better. Anything that's not gray in this picture means that you're exceeding the eutrophication limits that have been set by the European Union. So most of Europe is emitting too much nitrogen into the environment.
The what kind of limits?
Eutrophication. So we have a pretty good idea of how much can run off your fields before it starts causing lakes and marine waters to get all screwed up. And most of Europe is exceeding those levels. Exactly. This is what happens on land. The nitrogen falls out. These nitrogen-loving lichens and mosses take over your trees and make them ill. And in the oceans, in the Gulf of Mexico, you can see here the size of dead zones has been continuously increasing in the Gulf of Mexico because you're seeing the enormous watershed, which is a big chunk of the United States, drains into the Gulf of Mexico. The red zones is pollution from cities, basically sewage. The green zones is runoff from agriculture. And so you have a very large dead zone that forms in the Gulf of Mexico every year now, which is not a natural feature of the Gulf of Mexico. Here's a close-up of the Gulf of Mexico dead zone from, I think, a couple of years ago. Anything red is essentially there's no oxygen. Any creature that needs oxygen to survive, a fish or whatever, will die in that area, or will flee the area if it can.
Hey Jim, I hope I'm not stealing your thunder with this question, but what's worse, the annual nitrogen thing or an event like Deepwater Horizon?
It's an interesting question, and the results, the outcome of the Deepwater Horizon event are still unknown. Very large anoxic zone did appear after the immense deposition of oil into the Gulf of Mexico. The anaerobic bacteria loved it, and they devoured a huge amount of that oil, and that sucked oxygen out of the water while they were metabolizing that oil. But it's essentially a transient event, and so point events like that, transient events like that, typically don't have lasting effects on ecosystems. So it's these chronic, continuous injections that I think are much more worrisome. As you can see in this graph, it's a little busy, but it shows human population, as you can see, exponentially increasing. This is the knee of the exponential curve. And as a result, we've been dumping much larger quantities, teragrams, or millions of metric tons of nitrogen into the environment. And, of course, eutrophication follows. So here's a list of the documented dead zones caused by human activity. This graph is in 1989. And then by the year 2009, we had 400 of these hypoxia events. And the rate is we're about doubling the number of dead zones in the ocean every 10 years. So this is a form of geometric growth. This is not exponential growth. So this is something to the power of 2, right? This is 2x every year. But in another less than 10 years, we should have 800 dead zones. And 10 years after that, we'll have 1,600 dead zones. And so dead zones are essentially proliferating to take over the ocean. And I haven't gotten to carbon yet. So carbon is the element that we are disturbing most severely. Phosphorus is a very powerful element to be dumping into the environment, but carbon affects everything. And most importantly, carbon affects Earth's radiative balance with space, which means carbon, when you dump it into the atmosphere, warms the planet up. And it also warms the oceans up. So these are a number of different estimates to try to find out how much heat is being stored in the oceans as a result of global warming. And all of these various studies agree that yes, we are dumping more heat into the oceans. The heat's not stored evenly. Some places the ocean stores heat, like up here in the North Atlantic and off the coast of Asia. And a few places the ocean has actually gotten cooler. Not very many though. What effect does this have on ocean life? Well, if you can move, ocean life moves. So this is an interesting study that shows that the average movement is about almost 30 miles northward for northern hemisphere species. And a few species have actually moved southward toward the warmer. But most species are moving, or trying to move if they can. Which means that many of those species become invasive. This is a favorite new research that's just been done that shows red crabs in Antarctica invading parts of the Southern Ocean that they haven't been for 14 million years or longer. And I just love that creature. It just looks like something from War of the Worlds. And he's just walking along, devouring everything in his path. Things that he hasn't been able to eat, his species hasn't been able to eat for at least 14 million years. And there are many, many thousands of these crabs moving into the ocean floor in the Southern Ocean. Species, as the oceans warm, species that require sea ice are in trouble. Sea ice is going away. Even in Antarctica, the West Antarctic Peninsula, things are warming up and the ice is melting. Chinstrap penguins need the ice to live on, and as you can see, their numbers are declining drastically. Yes, these are the happy feet penguin. They're not so happy now. I'd like to talk more about the hydrologic cycle, which is affected by warming. I don't have time to talk about it, but I do want to note that a warmer world is a wetter world. So as the atmosphere warms, as the oceans warm, more water evaporates. And that water has to precipitate somewhere, on average 10 days later. And so what you see as the world gets warmer is you see bigger and bigger storms. You see more and more water dropped deeper and deeper inland as storms penetrate. For example, Alaska just had an enormous equivalent of a Category 3 hurricane just last week, dumping immense quantities of snow. So when people say that there was a big snowstorm, therefore global warming can't be real, keep in mind that there are still cold parts of the planet where you can get snow. And those parts of the planet, when you have much more wet air entering them, you're going to get a lot more snow. In addition to changes in the hydrologic cycle, you get more erosion. You get nutrients flushed into the oceans that wouldn't have been flushed into the oceans before. And also, depending on when the rains come, land life has to change its behavior. So the hydrologic cycle changes the phenology of species, which is the natural cycles, like when the flowers bloom and when the pollinating insects come to pollinate those flowers. Those kinds of cycles are falling out of sync now. But just as an example of what is happening with the hydrologic cycle, early this year, at the end of last year, there were very large record-breaking floods in Australia. A warmer world is a wetter world. And you can see in the lower right of this photo the Fitzroy River draining into the ocean, and the sediment plume is all going to rest on the great coral reef. So this is washing agricultural chemicals, pesticides, herbicides, nitrate, phosphate, all sorts of a stew of chemicals that could be directly lethal to the already very stressed coral reefs, but in addition can cause a bloom of starfish that eat the corals. And so they're worried in about 3 years there's going to be a huge increase in the number, probably an exponential increase in the number of starfish, and then they will devour the Great Barrier Reef. Carbon also makes the ocean more acidic. So this is from a Royal Society study in 2005 showing that more and more carbon dioxide is dissolving into the oceans, and it's following a nonlinear curve, probably a parabolic curve, it looks like to me. And of course the acidity of the ocean, the pH of the ocean is decreasing, meaning it's becoming more acidic. This is bad for a number of reasons. There was a similar event 55 million years ago called the Paleocene-Eocene thermal maximum. And on the left here you can see an ocean sediment core. And what's very interesting about this core, this is about 400 feet down. Before this event occurred, you can see this lighter clay. It's filled with millions of tiny skeletons of plankton that have calcium carbonate shells, calcareous shells. Then, an enormous amount of carbon dioxide was released, possibly by volcanic eruption, into the atmosphere. And that abruptly changed the ocean pH and made it more acidic. The result of that was for the next 50,000 years, those little organisms with their carbonate shells couldn't form anymore. It was too acidic for them to form shells, and so the entire base of the marine food web for this 50,000 year period was removed, with dire consequences for the marine food web. Something like 90% of marine life went extinct at that point. The next trophic level up on the food web, krill, they also don't do well in an acidic environment. As you can see here on the right, the krill embryos don't develop correctly. Also, shelled organisms, larger shell organisms that you can actually see, fail to develop their shells correctly in an acidified ocean. So this is an experiment where they took seawater in a tank and grew these little bivalves, these little mollusks, and at different levels of carbon dioxide and concentration, saw how well they growed. And as you can see, these right two, this is about where we're predicted to be by the end of this century, in kind of the best case scenario. In the worst case scenario, we're predicted to be about here. And as you can see, shell formation is much more difficult in an acidic ocean. So calling back to the Permian-Triassic extinction, we can actually start talking about what happened. What happened was there was an enormous eruption, volcanic eruption, called a flood basalt, or a rift volcanism. So a giant rift opened up in what is today Siberia, and for about 1 million years dumped carbon dioxide into the atmosphere. And what's interesting about this research, this is very new research, they went to a lake in Canada, what is now Canada, called Buchanan Lake, and they were able to find the layer where this gigantic volcanic eruption deposited fly ash, what is essentially comes out of our coal plants. So at Buchanan Lake, a 250 million year old sample looks very much like what comes out of our modern coal power plants. And what the theory now is that this gigantic volcanic eruption hit a huge coal seam and proceeded to burn an immense quantity of coal, just by coincidence, and liberate huge amounts of previously sequestered carbon into the atmosphere. It's estimated that the Siberian eruption emitted some 3 teratons of carbon over about 1 million years, which is about 3 million tons of carbon per year. Humans have emitted something like 1 trillion tons of carbon in the last 100 to 200 years. We're currently emitting about 9 billion tons of carbon per year, which means that we are emitting at a rate some thousands of times greater than the worst mass extinction event on Earth. So going back to our diagram of the marine food web, after everything that we've discussed here, how does it look? Looks bad for plankton, the base of the food web. They're being destroyed by acidification of the oceans. Bottom trawling is removing entire benthic communities, invertebrates and fish. Pelagic longlines are removing most of the large fish and many of the smaller fish, the mesopelagics. Acidification is also going after krill. As you saw, the krill embryos don't do well in acidified oceans. And also the craze for omega-3 fish oil now is driving krill fisheries. So now we are capturing immense quantities of krill and using them to fix ourselves, which puts us in direct competition with all of the other species that eat those krill. So that paints a pretty bleak picture. Who's doing well? Opportunistic species are doing well. You may know about the Humboldt giant squid. I don't know if you've ever seen some photos of those. They've been making appearances very much further north along our coast than they ever have in the past. They're pack hunters, and they're big, mean-looking creatures that are just delightful. They're doing very well. There's another species of squid called Vampirotuthis, which does very well. Yes, it's named because it looks like it's a little black vampire with blue eyes. It's a beautiful creature. I don't have it here. They do very well down in anoxic water, down to 3% oxygen. They're doing very well. And jellies, of course, are doing extremely well. Also, microbes. So, what we are seeing is anaerobic microbes love the new environment that we're creating. These are the most ancient forms of life. They're cyanobacteria, they're the decomposing bacteria. They existed on Earth before we had a largely oxygen atmosphere. In fact, they're responsible for turning the atmosphere into a largely oxygen atmosphere, which was a large catastrophe for them, but worked out nicely for us. So what we're seeing here are purple sulfur bacteria, and these sulfur bacteria eat the hydrogen sulfide that's being produced by decomposing bacteria that are down in the sediment underneath them here. They love living in an environment where there's no oxygen. So this is a diagram that shows what the Earth might have looked like at the end Permian extinction when the oceans essentially died. The oceans were taken over by those purple bacteria and other forms of anaerobic microbes. And most multicellular life in the oceans died, either because of anoxia or because of the toxins that the microbes emit. Here's an example. I just threw this in as an example of what a red tide looks like off the coast of the Scripps Oceanographic Institute. This shows you an idea of how rapidly the oceans are becoming anoxic. Gigantic swaths of the oceans now are becoming uninhabitable by species that require oxygen to survive. There's a similar anoxic zone off the west coast of Africa. This shows you the zone of about 10-meter thickness, I think. That's what the 10 represents here, where there's essentially no oxygen, so none of the life that we think of as familiar and friendly can live there. As the oceanographer at Scripps, Jeremy Jackson, says, the future is bright for dinoflagellates. So we're creating an environment in which unicellular life, single-celled life, loves what we're doing. I sometimes wonder if our brains haven't been taken over by some species of anaerobic bacterium and are directing us down this path to return the Earth to the way it was some billions of years ago. I just like this photo of this is a red tide algae, a long exposure photo of this toxic algae making the ocean water glow at night. So what are our prospects? The end Permian extinction, biodiversity didn't recover for some 5 to 10 million years, which is essentially forever on a human time scale. The human species is perhaps 200,000 years old. We can talk a little bit about what humans are doing with coal, talk a little bit about human population, and possible solutions. Unfortunately, the future looks grim for fossil fuel use. Our dependence on fossil fuel is ever greater. There have been a number of attempts to wean humans from fossil fuels, but unfortunately, we just found out a few weeks ago that the total human carbon emissions has increased from about 7 gigatons per year just a few years ago to 9 gigatons per year now. So all of our efforts to reduce our carbon footprint apparently have been for naught, and we're going to continue to burn coal into the foreseeable future. We might look at this isolated reindeer population that occurred right after World War II on a place called St. Matthew Island. There were no reindeer on St. Matthew Island before 1944. And then a population of, I think, 24 was dropped onto the island, just for the fun of it, apparently. And they had no natural predators, and they had big mats of lichen, which is their favorite food. And so these reindeer reproduced Similarly, for human beings, you can see the exponential rate of growth of the human population. We have no natural predators to control us, and we have fossil fuels to feed us. And so, of course, our rate of growth is exponential. And I had to tack on a little more to this graph. This is an older graph from the Census Bureau. So we just crossed 7 billion like 2 weeks ago. And so, as you can see, we're in no way capable of controlling our population. So nature will control our population for us.
So Jim, I assume you're somewhat skeptical of the mainstream response to population reaching 7 billion, which is there's really not a population problem. It's going to peak out at about 8 or 9 billion and just level off for a long time.
The standard S-shaped curve that we talk about usually has human population peaking around 9 to 10 billion, but the UN just came out with a report like 2 weeks ago saying that the population is likely to be 15 billion by the end of this century. Clearly, as I mentioned a couple times, exponential growth in any physical system cannot be sustained indefinitely.
Without additional energy inputs.
Well, something's going to break. I
Right.
mean, in any physical system, even if it's like flight controls on an airplane, in engineering we say that the system is departing whenever you see those kinds of curves, and they mean that your control system has failed. And so something's going to give. And what it's going to be, I don't know. I expect that we will simply destabilize the climate to the point where agriculture fails. And once agriculture fails, then it won't matter how much fossil fuel you have. But just as an aside, we have here the Koch brothers. Some of you might know of David and Charles Koch. They're ably representing the fossil fuel industry. My theory is that by about 2008, the Al Gore message was actually getting traction in the United States and elsewhere. And this is very alarming with the fossil fuel industry. As far as the fossil fuel industry is concerned, we need to keep digging up that carbon that's been safely sequestered for millions of years and burning it. That is the only imperative, is to keep burning coal, keep burning oil. And if there's any trend toward us not burning coal and oil, that's very, very bad for business. So as a result, every night on television, you can see on broadcast television, you can see Ms. Brooke Alexander, and she is representing the American Petroleum Institute, and every night she tells you how oil creates jobs, how we should embrace oil, we need to pump more oil, and it's good for the economy. Which, is true if short-sighted. By about 2008, the fossil fuel industry had decided they needed to spend hundreds of millions of dollars lobbying Congress to keep burning the oil, keep digging up the coal. And environmental groups can lobby Congress as well, but they're being outspent, as of 2009, they were being outspent at about a rate of 8 to 1. So it's really impossible for environmental causes to get their cause heard by Congress because they're just being drowned out by all of the fossil fuel money.
Why is there less in 2011?
I got this graph from a few months ago. I think they hadn't collated the data yet. I would expect that in 2012 it'll probably break all of those records. That's fine. You might even see a bit of an, almost exponential curve there. So I'm going to talk a little bit about what might be done. Putting all of the fossil fuel industry lobbying aside, what could help? So what could help is we stop discharging hundreds of millions of tons of sewage into the oceans every year. That's doable. 90% of sewage in the developing world is untreated. What does it take to treat all of this wastewater? The United Nations estimates that it probably takes somewhere in the neighborhood of $800 billion, $870 billion to treat all sewage and wastewater globally. And
That's
put that,
jobs.
yeah, exactly.
That's
Sure, you know it.
From sewage plants.
Right, exactly. Build sewage plants. And for comparison, the cost of the Iraq War is about $800 billion. So it is conceivable that we could actually stop dumping sewage into the oceans at the rate of gigatons if we got our act together. This is part of the Millennium Development Goals for the United Nations, which there was a report that came out this year that showed that we're falling woefully short of all of the development goals. So there's just no human appetite to fix these problems. So this seems like it's out of left field, but what I want to talk about now is solutions that I can believe in. I don't believe in a lot. I'm very skeptical of many of the purported fixes that we hear about. Solar, great. Wind power, great. I don't think any of that's going to scale in a way that's going to save us. It's not going to happen in time. But there is a device called an atmospheric vortex engine. And it exploits the idea that there's a very large temperature difference between the surface of the Earth and the tropopause, which is the top of the troposphere, and that you can actually build a heat engine, exploit a Carnot cycle to extract power. So this is a picture of a supercell. It does the same thing. It's on a smaller scale than a hurricane, but it basically takes heat that's stored in the form of water vapor and creates a vortex that carries all of this heat to the top of the atmosphere and then dumps it into space. So an engineer in Canada has come up with an idea for harnessing this idea and building a power plant. This would be about a 200 megawatt power plant. It runs on, once you've kicked it off, it runs on nothing but this large vortex, a tornado essentially, that you create from the ground to the top of the atmosphere. And if you built millions of these devices, you could both power civilization and, perhaps more importantly, export heat directly to space. We have no way right now of exporting the excess heat that our atmosphere and oceans are retaining to space, which is what's important. And this would give us a way of creating valves that would let us vent extra heat to space. The other problem is ocean acidification. What do we do about that? So there's an outfit in Australia called sequestrate, and what they're proposing is that we take calcium carbonate, limestone, dig it up in gigaton quantities, cook it to extract the lime, the calcium oxide, and dump in gigaton quantities, dump that lime into the oceans. This has the effect of both making the oceans less acidic, and it also fixes the carbon into a form that is not bioavailable and will be taken out of the system essentially forever. Well, how do you do that? You go to the Null Arbor Plain in Australia, which is a giant chunk of limestone, down here shown in red, and you start digging. That's what it looks like from space. And this is many billions of tons of limestone. What I would propose is that we put atmospheric vortex engines there to power the entire process. And then we dig up and cook the limestone and dump it into the oceans. Beyond that, I don't see very many solutions that can scale fast enough or have even any chance of making a dent in the problem.
Explain atmospheric vortex.
Atmospheric vortex machines. So what's interesting about this device is that when the sun shines on water, on the oceans particularly, the water evaporates. That water vapor is essentially fuel. It's holding all of this solar energy, and that's what drives hurricanes and other storms. So a hurricane is a giant heat engine. And if you could put a turbine somewhere in a hurricane, you could power most of civilization, or a lot of civilization. So we don't, maybe not on the scale of a hurricane, but we can create a smaller sort of system that takes all of that water vapor, condenses it into a vortical tunnel, a tornado essentially, and when that water vapor condenses into water droplets, it releases heat. And that causes the air to be carried up. It makes the air a little bit warmer wherever a little droplet condenses. And that little bit of warmer air will go upward because it's more buoyant, it's less dense. And so if you can make a stable structure that will allow basically a giant chimney to the edge of the atmosphere, you can exploit all of that water vapor fuel. And that's what we're proposing with the atmospheric vortex engine.
Wow.
How high would that be?
The top of the troposphere, which is 10, 12 miles.
No, I mean
The chimney itself doesn't have to be very high. You need to make sure the vortex can be stable, so I think the estimates are like 40 meters for the chimney itself. And then the vortex itself, it remains stable all the way up to the edge of the atmosphere.
Yeah.
Could you give us an idea of what's
weird.
You would? Pardon me?
what size thunderstorm, if you will, would that?
You would indeed. You would create a permanent supercell over your power plant.
Right.
And so there'd be continuous rain downwind, and probably lightning too. But that could be exploitable too. You can use that rain. You could use it for crops.
All that, how big a storm, and I'm calling it that for lack of another word, would it take to supply the power for this city?
One of these units is around 200 megawatts, is the plate power. Houses consume something in the range of 5 kilowatts. So you could power a lot of houses, whatever 200 megawatt divided by 5 kilowatts is. Do that 40 megawatt, 40,000, I think, 40,000 homes, something like that. And my thinking is that you would build as many as you need. You know, in the industrial model, 1 million of anything is not very much, right, in the industrial paradigm. And so building 1 million of these things should actually be entirely doable. Of course, you need fossil fuels to build them to start with. So you have an initial investment of fossil fuel energy. But once they're built, they don't take any energy at all. They just take the latent heat out of the water vapor that's in the air. But aside from powering society, even more important to me is the idea that you have a pipe directly to space for heat. I've often said that you need to basically refrigerate the Arctic. I didn't talk about it in this presentation, but there's about 1 trillion tons of carbon locked up in the permafrost, and all of that permafrost is melting now. Probably the biggest threat we face next to our own fossil fuel emissions of carbon. That's carbon that's been locked up in the permafrost for millions of years. And we're about to liberate it. We are liberating it now on a scale that no one has really measured it. But that carbon is coming out, and to have a healthy Earth, we have to have a frozen Arctic. And so exporting heat from the Arctic to space would be a very useful thing. I don't know if you could use an atmospheric vortex engine to do it. I've often thought we can use lasers as another way of conveying energy from the surface out to space. So I've sometimes asked Isabel what it would take to create an illustration showing an Earth with thousands of green laser beams spewing out from a crown of thorns, if you will, from the top of the Earth, radiating energy into space. That's a little more fanciful than the vortex engine idea, which you can do with today's technology.
Jim, don't you think you should distill one pipe dream, and that's the idea? If you get up to the maximum number of people that there's going to be, which I question is when you get to 9 billion, then the idea will flatten off is nonsense.
Indeed. Well,
it's going to go, when those things get to a peak, they do what you said, they crash.
I believe that humans are just another species. And we may believe that we are decoupled from... excuse me, question? Yes?
I'm curious about what projections are there as to how long it would take to deplete that limestone supply in Australia?
Apparently, it would take a long time. The calculations that I've seen...
Centuries?
Probably. The problem, of course, is that you need to stop emitting the carbon, right? Otherwise, you're on a treadmill.
Exactly.
And so the best solution, of course, is to stop emitting carbon. But if we stop emitting carbon tomorrow, we still have a lot of heating in the pipeline. So the warming that we're experiencing today is from carbon that was emitted 30 years ago. And so there's nothing that replaces stopping carbon emissions. You have to do that.
Is there now,
Oh, sorry, I'll get to you.
is there now underway, or has there been an effort at all up to now to convince people like the Koch brothers and their congressional sponsors that there is a tremendous economic opportunity in reversing this trend?
I'm sure there is. Al Gore's organization, I think, is a good organization. They try to get that message out. There's institutional schizophrenia in a number of ways, though. For example, Rupert Murdoch's organization, who owns Fox News, they've sent out letters to their employees saying how they want to be good corporate citizens and they want to control their own carbon emissions, which is great. But at the same time, they use their media outlets to spread the message of global warming denial. So yes, this kind of disconnect is quite common, I'm sad to say. Oh, I'm almost done, but I'll get through these last couple slides. So things that you can do today. At some point, I had considered not even bothering with this part of the presentation because it looks pretty hopeless to me. But I can't leave an audience, dragging their feet on the way out toward their doom. So things that I can suggest that you can do today. There's this interesting outfit. They do the ecumenical Lenten carbon fast. So Lent, if any of you observe Lent, you might consider giving up carbon for a few days, or you might consider buying carbon offsets. I buy carbon offsets from Native Energy because they install energy production facilities on Native American lands. cogeneration facilities, wind turbines, that sort of thing. So those are possibilities. Other things that you might want to keep in mind is to buy only sustainable seafood. I have anybody's interested in the Monterey Bay Aquarium's list of sustainably harvested fish species. I have
That's
that here.
also in the Chinook book.
Oh, good.
And they have an app.
And they do have an app, yes, so you can install that. I always say never use pesticides or herbicides or fertilizers, ever. Only do organic farming or gardening or however you do that. Always use phosphate-free detergent. We don't want biologically active phosphorus being emitted into the environment at all. Buy organic, recycle, use public transportation, reduce or eliminate air travel. These are the commonly accepted things that you can do personally in your life to reduce your carbon footprint and possibly avert catastrophe. So there's a list of a few resources, and now I can take some questions. I wasn't. There's a lot of things I took out of the presentation, but I can to whatever degree of interest there is.
Is there one of these vortex generators you're talking about in existence working now?
No. There are a number of prototypes that's been built by the engineer, Luis Michaud, and the idea itself has been vetted by a number of pretty prominent engineers. There have been a couple of solar chimney projects that have been built, which are conceptually somewhat similar. There's an Australian company that is building a solar chimney that's essentially a large concrete tube with a skirt that's a greenhouse a couple of miles wide. And the greenhouse skirt heats up the air, and then the hot air is funneled through the chimney, and there's a turbine at the bottom. Kind of a similar idea. There was one also built in Manzanera, Spain, by a German architectural firm, a much smaller, like a 50 kilowatt model, which worked quite well for a number of years. So those ideas have been shown to be plausible. There are some concerns around air traffic, like you have to route the air traffic around this permanent supercell that's sitting there wherever you decide to build these things. But those are manageable problems, and the rainfall and the lightning problems are probably quite manageable. In fact, it could be used to generate power, water.
Could you go back to the previous slide? This one's not visible. Great, thank you.
If you're curious about the background image, that's the Christ of the Abyss in the Mediterranean Sea. I think it's appropriate.
James, what are the universities of the world, namely some of the chief engineering universities of the world, what are their contributions as engineers? Since that's where your thought process is coming from as well. I mean,
There's the first oil emissions. You can get another gigaton of emissions by economizing, by energy reduction. Unfortunately, he had 7 wedges a few years ago. Now it's 9 wedges because our emissions have increased so greatly over the last couple of years. That's the first engineering effort that comes to mind. Yes?
I'm involved with the Hood Canal cleanup
Oh, good.
a little bit.
Excellent.
And what we found early on with the contribution of those buoys from the applied physics lab is we had assumptions about how that place worked, and they were absolutely wrong.
Yes, that's typical.
Yeah, you answered my question. Is there a movement to really understand this stuff? Because we clearly do not at this moment. Your
movement.
as clearly as I've ever heard it explained.
Oh, well, thank you very much. There's a great deal of scientific interest. All of the stuff I'm showing you today is pulled out of peer-reviewed scientific papers. So there's a lot of scientific interest in these various aspects of these problems. There's even some scientific interest in synthesizing a holistic view of these problems. I would say we're a long way from a movement, however. Probably Al Gore's organization is the closest thing to a movement that you might see, where he actually has people come to a central point and he teaches them how to talk about these issues, and then sends them out to their communities, and they have individual community presentations, kind of like this. Whether there's a movement that will have a critical mass enough to actually make a difference, again, in the face of exponentially increasing population and all the other exponential curves that we're up against, I don't know. The belief in global warming which is a strange phrase to me. It's like belief in gravity, you know. Believing in thermodynamics is, I mean, it's not a matter of belief. It's a matter of fact. This computer would not work if we didn't understand thermodynamics. And the physics of global warming is exactly the same mathematics as the physics of heat propagation in that computer. And so if we didn't understand thermodynamics, that computer wouldn't work. And similarly, we wouldn't be able to predict the temperatures of bodies in space. Mars, Venus, stars, exotic bodies like the moon Titan around Saturn. If we did not understand thermodynamics well enough, we would not be able to so precisely compute the temperatures of those bodies. So when people say the global warming is a matter of belief, they just simply don't understand the science behind it, the physics behind it.
Is it?
Right. Yes, ma'am.
I think
What I
this will be our
find
last
myself
question.
wishing for is a printout of your PowerPoint presentation, or having it available like on a website.
I'll post it, yeah, totally. So you'll be able to download it.
Thank you.
I want to thank Jim for coming.
Oh, thank you.
This is our last Earth Bistro for this quarter, but I think we've decided, the Sacred Earth Group has decided that we'd like to offer the one Earth Bistro probably once a quarter. It seems to be ringing true that people enjoy coming to stuff like this, so I think we'll go forth with that. So look forward to something coming in January. And thank you all for supporting it and for coming. It's just been a marvelous experience for all of us, and our speakers have been just outstanding. So thank you.